Hey, that's a good bit rate. All right. All right. I don't think Twitch is working just yet. Beep, beep, beep. Whatever, we don't need it. I'll just stream on YouTube and Twitch will probably figure itself out. Yeah. Okay. Sweet. Well, it's that time again. It's time for abelian grouper time. And since it's Thursday, that means it's time for Group Theory Thursday. Group Theory Thursday! And since it's the first week of Group Theory Thursdays, we'll start from the beginning. And so if you're tuning into Group Theory Thursdays, thanks so much for tuning in. And if you're not, thanks for not. But whatever. Anyhow. So what are groups? Well, groups are what we're going to talk about, and they're the foundation of abstract algebra, and they're one of my favorite things in mathematics. They're also the source of the abelian grouper's title. And so without wasting tons and tons of time, let's take a look. So what we're going to talk about today, we're going to start by talking about the integers. We'll talk about modular arithmetic, and we'll mod out the integers, so to speak. And then we'll use these two examples to motivate the definition of a group. And then we'll talk about the order of a group and the order of an element of a group. And then we'll do problem sesh, brah. So we'll sesh through some problems. It'll be chill. So let's start with the integers, yeah. The integers are... well, they're just exactly what you think they are. They're all the positive and whole numbers, whole numbers, negative whole numbers, and zero. And there they are, written as a set. We're going to use this uppercase. It's called Blackboard Bold font here to indicate the integers. So Z, I think that's from a German origin, but whatever. Z integers. And so the first thing we'll notice about them is that if we just add two of them together, we always get another one. And a fancy way of saying that is that the integers are closed under addition. And what that means is just exactly what I said. Like if you add two integers together, you get another integer. And the cycle of life continues. Right? Like 2 plus 3 is 5, 5 plus 7 is 12. 6 plus negative 7 is minus 1, etc., etc. But no matter what you do, you're not going to somehow lose the integers, right? You're not going to have the integers and then add two of them together and somehow get 1/5, right? Like you can't add two integers and get pi. So it's closed. That's important, right? Another nice property of the integers is that if we take three of them, or any finite number of them, in point of fact, we can order them in whatever order we want to and add them together and we get the same result. Yeah? And to make this maybe potentially slightly less abstract, let's just see exactly what this means, right? So if you had, say, like 2 plus 3 plus 5, right? I mean, it doesn't matter if I add 3 and 5 together first, right? This is, 2 plus 8, which is 10, right? But alternatively, if I add 2 plus 3 first, Well, that's just what, 5 plus 5. And again, that's 10, right? And to those of you who've ever, like, you know, done algebra in high school or whatever, this probably seems pretty trivial and like, well, yeah. And that's true. It is kind of like, yeah. But it's a nice thing to note because there are places where this doesn't happen. You don't always have associativity, and when you lose it, things get rough. It's the world of Lie algebras. But anyway, so the integers have that. It's very nice. It's very nice. Yes. So yeah, so associativity. This is key. We also, 0 is in there, and 0 has this really nice property with regards to the rest of the integers, and that if you just add it to any integer, you don't change anything, right? Like, you're always going to have whatever you started with. So like 2 plus 0 is the same as 0 plus 2. You always get 2 again. 5 plus 0 is 5. 8 plus 0 is 8. Negative 6 plus 0 is 6. Negative 6, right? So on and so on. Even 0 plus 0 is 0. 0 unchanges itself, yeah? And so it's an identity. It preserves the identity of whatever else you operate it with, yeah? Good times. Good times. Another nice thing about the integers is that you can always find an inverse. So if you take any integer, any whole number, you can always find an additive inverse. So exactly like we see there, right? N plus minus n is 0. But similarly, right, I mean, negative 7, its additive inverse is positive 7. It's just the opposites, right? Yeah, and again, we all know this, right? It's not that it's surprising. Also, it's worth mentioning here that these inverses are also unique, right? Like, if you choose 2, there's only one thing there's only one inverse, right? There's only one way to get back to 0 from 2. Or similarly, like, there's only one way to get back to 0 from, like, negative 47, right? Or 200 billion. Or 11 trillion. Or whatever. But we'll prove that inverses are unique. Not just for this, but we'll see in more general that they happen to be. But anyway, these properties, if we put them all together, we see that if we take the integers as a set and we put them together with this operation of just regular addition, we have this associative binary operation from z cross z back into z. That's a typo there. I'll fix that later. It admits both an identity and an inverse. Yeah. So let's keep those. Let's just keep that sort of rolling around in the back of your mind as we roll to the next example, and that's modular arithmetic. Whoops. So modular arithmetic kind of changed the game back in the day. Like, before modular arithmetic, number theory had kind of just gotten stuck. You couldn't describe things without a better notation. And modular arithmetic allowed us to abstract relationships between integers in ways that were not previously possible. And it's amazing how notation completely progressed mathematics more than anything else. It was the notation among all those else. The notation. Whatever. Anyway, so, right. But before we get to modular arithmetic itself, let's start with, and it is in our lives all the time. Modular arithmetic is what happens. It's how we use clocks. It's how we tell what day of the week it is, or what month of the year it is. Yeah, so if you have something it's cyclic, modular arithmetic is a good way to deal with it. Assuming it's also discrete or whatever. Anyhow, so let's get some technical business out of the way first. We have to define a little number theory notion here. So if we have two integers, a and b, we say that a divides b if and only if there is another integer, let's just call it q, such that b equals a times q. Right? And if you think about it, I mean, this makes sense, right? It's saying like this number b is the same as a times q, so you could divide by a, and you would still get an integer, right? You get this integer q back, right? There's always a danger, like if you try to divide two integers as opposed to adding them, right? Like if you try to divide two integers, you can very quickly come up with something that's not an integer, right? So if you try to take 2 and divide it by 5, I mean, you get 2/5, and that's all fine and good, but it's no longer an integer, right? Like you've lost that bit, alas. Whatevs. But anyway, so divide, it sort of means what you think it should mean. We don't really allow for remainders in this sort of normal sense. A little bit later, we'll see there's something called the division algorithm, and that sort of handles that. But yeah, this notion of divides is, you could say this is where like all of modern number theory kind of springs from. And then, more importantly, this is the biggie. This is the modular part, the modulus. So if we fix some integer n, right, and we take two other integers, just a and b, any ones they are, we say that a is congruent to b modulo n, and we write it with those three little equal signs there, and then the mod n, if and only if n divides the difference of b and a. This forms an equivalence relation, and so what would you have to do to show that it's an equivalence relation, right? You'd have to show that it's symmetric and transitive and reflexive, right? So it's all going to come down to just going back to using this equation, right? Like, you know, if n divides b minus a, that means b minus a equals n times some number, right? And so that's sort of where you jump off from, right? Like, you know, you can just write down some equations, yeah, and then you'll eventually just factor out n's, and you know, it's not bad. But in a more intuitive sense, what this means is that two integers are congruent modulo n if and only if they're a scalar multiple of n apart from one another. And so to try to visualize what that means, let's pull out the old pen and paper here, the old-fashioned style. All right, and let's maybe adjust the light real quick. That's better. Cool. Ow. All right. So forget all this. So to sort of think about what modulo means, right? Like, let's just line up a bunch of integers here, like minus 10, minus 9. Boop, boop, doop. Boop, boop, doop, doop, boop, 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 doop, boop, doop. Let's go down to 0. So here's some integers, just sort of lined up, yeah. I don't know why I didn't just start at 0 and go positive, but it doesn't matter. So let's say, for example, let's choose, say, -9 and -6. Yeah. Well, I say that -9 is congruent to -6 mod 3. In part because they're exactly 3. You know, from the intuitive sense, it's because right, intuitively, it's because those numbers are 3 apart. Yeah. We can also see it from the definition of our little equation, right? So if, you know, -9 minus 6 equals 3 times something, right? Well, what is this? This is, what, -15 equals 3 times k. Well, sure, then k equals -5. So there does exist such an integer, yeah? And so these are congruent, modulo 3. That's obvious because they're both multiples of 3. I mean, maybe it's not too surprising. But what about this? Like, what about -7 and -4? Well, it's the same thing. These are also congruent. Mod 3 for the same reason. They're 3 apart. And yeah. Well, actually, silly. I mean, it actually doesn't matter. That's embarrassing. There we go. Forgot the minus sign there. But here in this case, right, when my brain's turned on, -7 minus a -4 is +4. Well, what is that? That's -3, which is, again, 3 times -1. So it's coincidence that both of these are -1, but more importantly, geometrically, the notion is this, that, well, not geometrically, but sort of visually, right, is that if they're 3 apart, they're in the same congruence class. But it's not just if they're 3 apart, it's if they're any multiple of 3 apart. So for example, right, I can just come 3 over more, and I can see that -10 is also congruent to -7, which is also congruent to -4. Now, since we know these two are congruent, if these two are, we know these have to be, since congruence is an equivalence relation. But also, like, it's just another multiple of 3, right? We could do the same, right, if we're sort of running out of space here. But like if we did 5 to -5 to -2, right? Those are 3 apart. Let's look at another one. So in particular, let's just do like -6. Cool. Look at that. Excellent spacing. Excellent spacing. So here's a bunch of integers, right? So notice that, again, let's go mod 3 again. So let's start from 0. Yeah? So we know that 0 will be congruent to everything that is a multiple of 3 away from 0. So that's 3, 6, 9, 12, 15, 18, 21, blah, 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 out for infinity. But if we go the other direction, -3, -6, -9, -12, -8, 15, 18, blah, 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 blah. So 0 is congruent to just all multiples of k mod 3. Yeah. So all of these guys are all in this. They're all the same modulus. They're all equivalent to 0 mod 3. Similar. So we've got, essentially, that means a third of the integers are covered, right? Also, if you know what an equivalence relation is, you know this is going to form a partition. So it's maybe already be obvious where this is going. But let's just go over to 1 now. So if we think about 1, well, the equivalence class, the stuff that's congruent to 1 is going to be 3 units away from 1 and multiples of 3 units away from 1, right? So that's going to be like 4 -2 -5, right? So 1 will be congruent to all the 3k plus 1 stuff. And then the other stuff, right, like 2, 5, -1, -4, -7, blah, blah, blah. That stuff's all going to be congruent to 2. Boom, chicka, boom, chicka, boom, boom. Yeah. So another way to think about this is, if you know what the division algorithm is, these are the remainders, essentially, when you divide by 3. And they're the only possible remainders when you divide by 3, right? Like if you divide some whole number by 3, well, if it's a multiple of 3, you get a remainder of 0. If it's one of these numbers, like 1 or 4 or 7, and well, then there's a remainder of 1, and then if you have like 2 or 5, there's a remainder of 2. And so this partitions the entire set of integers into these 3 classes, and we can denote these classes. I don't know why I talk like that sometimes, but like we can denote these classes, like so 0 class. This is the set of all 3k. So that k is in z. There's different ways to think about this, but and then similarly the 1 class, the set of all 3k plus 1. There's that 1. I mean, sort of here. I'm being a little loose maybe with my notions. I mean, it's, yeah. No, that's fine. That's fine, I think. Whatever. Same thing. Yada, yada, yada. Zip, zap, zooble. Yeah. Sweet. So yeah, so we can define these equivalence classes. These are the equivalence classes that you get from partitioning the integers modulo 3. 0, 1, and 2. And it's essentially the possible remainders. It's a good way to think about it, I think. But yeah. So it's not too hard to believe, right? I mean, so in mod 3, there's exactly 3 equivalence classes. If we go up to mod 4, let's skip mod 4 for right now. Let's do mod 5. So like if we do mod 5, right? Well, okay, so there'll be the 0 class. You have 0 class, Janine. Anyway, and the 0 class, right? Well, this is just all the 5k stuff, right? I'm going to just be lazy with my notation. K is an integer, right? And then you'll have the 1 class, which is the 5k plus 1. 2, 3, 4 class. I'm not going to write all the rest out. I mean, they're exactly right. It's 5k plus 2, 5k plus 3, 5k plus 4, right? And so, yeah, we get this. So we can do this for any integer, right? We can do it for 12, 57, and so on. Strictly speaking, I mean, you really only want to do this where n is positive. I guess I should have put that in the. Maybe I'll change that later. But anyway, the idea is the same, right? It's just equivalence classes. And these equivalence classes, it turns out, have some really nice properties. So let's stick with this mod 5 one here. We'll keep that in our memory banks. And yeah. So what we want to actually do is we want to do something with these, right? So we have these equivalence classes. I'm definitely like waving my hands in the air that stuff is well defined here. We'll definitely do a lot of that lately. But when we get into normal subgroups in a couple of weeks, we'll be able to define these concepts and grip them all firmly and wrangle them into, perfect logical alignment. When we start talking about normal subgroups and homomorphisms, we can talk about all this stuff more generally. But anyway, you can just use basic number theory stuff to prove all of this is well defined, but we'll see some other stuff better later, I think. A better perspective anyway. Anywho, so if we have one of these, I want to define an operation on it. So let's define this operation where if I have 2 of these equivalence classes and I add them together, then I just add their sort of components together and choose that equivalence class. So let's see what that would look like. Let's go back to Z5 here for a second. Incidentally, yeah, so there's our notation. I'm just going to always use Zn probably when I talk about one of these modulo collections. It's just the notation I learned it with. I also think it's nice and succinct. Succinct. Yeah. Anyway, so for example, so this modulo 5 stuff, we can call it Z5, right? And it's this set, the 0 class, the 1 class, the 2 class, the 3 class, and the 4 class. Yes, yes? And based on our definition, right, which you can still see there, we just define, so for example, like the 1 class plus the 2 class, well, that's the 1 plus 2 class, which is the same as the 3 class, right? That's cool. That's cool. Now, this is the place where I'm definitely just waving my hands that this is well defined. And the reason for that is, you know, I'm saying, okay, here's the class with all the stuff that has remainder 1 when divided by 5. And here's all the stuff that has remainder 2 when divided by 5. Both of these things are equivalence classes with infinitely many objects inside of them. And so, you know, the 1 class is the same as the 6 class, is the same as the 11 class, right? And the 2 class is the same as the 7 class, is the same class as the 12 class, and blah, 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 blah. Right? So if we chose different representatives for this class, would we necessarily get the same thing at the end? And it turns out the answer is yes. It's not horribly difficult to prove, actually. It's just a matter of doing it, and I don't really want to, again, because this stuff will come up later, I think, a little more naturally in terms of well definition and all that. But yeah, so this is all fine and good, right? But what if we had something like this? Well, this is the 7 class, right? Ma, what does it mean? What could it do? Where could he be? 3PO. 3PO. Whatever. Anyway, but what is the 7 class? What is... Okay, so this is the class with 7 in it. Well, what is 7 modulo 5? Well, it's 2. Bam. Isn't that awesome? In this Z5 universe, 4 plus 3 equals 2. Nah. 2 plus 3 equals 0. Whoa. Anyway. But yeah, so again, there's some stuff to be proven here, right? That this addition actually makes sense. It does. You know, it's kind of the foundation of lots of stuff, but it's I'm not just like totally ignoring it. I'm just ignoring it for now. Oh wow, yeah, I did all that by paper, and I already actually typed it out. But anyway, this is good though. So here's more with Z5 again, right? I'm not going to do the overlines again. That's pretty standard. Like anytime you see, you know, Z mod NZ or ZN, in this case, the way I'm writing it, it's just assumed that, you know, contextually that those are equivalence classes. So yeah, those are the equivalence classes, right? And what's important is that the 0 class, right, based on our definition of how we add, right? Whoops. Right, we add by, you know, taking these two representatives, combining them, and taking that new equivalence class. So if we take the, So if we take the 0 class and we add it to anything, it's not going to change the representative, so it's certainly not going to change the class. So we have an identity element, right? We have this 0 thing that doesn't change the classes. Also, as you can see in this cool world, like 2 plus 3 equals 5, which is the same as 0, so 2 plus 3 is 0. More importantly, though, we see that 2 plus 3 has an inverse, right? Or 2 and 3 are inverses of each other, right? 2 plus 3 is 5, 3 plus 2 is 5, right? Those are inverses of each other. They go back to that identity. 1 plus 4 is the other pair, right? And then, you know, it's not hard to believe those last little bits, showing closure of this addition. You're never going to get out of modulo 5, right? There's no way you can add two things modulo 5 and somehow get something modulo 12. Like, it doesn't work that way, so that's fine. Associativity you should show, but again, that's going back to that well-definedness business that we'll handle later. But the idea is, earlier on, I told you back when we were talking about just the plain old integers, to think about, like, what are these things? God, I've got to stop doing that. All right. All right, so, it have these same properties, right? There's a 0, there are inverses, there is associativity, and there's closure, right? And that's how we come up with the definition of a group, and it's defined axiomatically. Oh man, that didn't compile how I wanted it to. Whatevs. Anyway, so a group G, comma star is a set G with a binary operation. And a binary operation just means, right, that you take two things from G and they live inside the Cartesian product there. So essentially that's a ordered pair of elements from G, and that maps them back into a single element of G. And the following things have to hold. The operation has to be associative, right? Just like the integers were. We have to have an identity element. I'm using E here. That's a pretty standard generic. And the reason for that is because groups, at least the interesting ones, or the more exotic ones anyway, tend not to be just like numbers. They tend to be some weird thing to do with numbers, or I don't know. They're just something. But anyway, so what that identity is can vary quite a bit, and we'll see that in the problem sesh. So it could be a matrix, it could be a function, it could be a permutation, it could be all sorts of things. And then finally, the other one is we need to have inverses. So if we have all of these things, then we have a group. And so what we just saw were two examples of groups. Because, as we discussed, right, like they both have these properties. There's the discussion of those properties that motivated us to come this far and define this. And historically, that's, I think, probably part of the motivation for this. I mean, there was a lot of different things that sort of gave rise to group theory throughout history, all over the world, really. I mean, the Middle East, Persia, and at different times, like, I know rabbis in Israel were studying the Talmud, like, and that gave birth to, like, permutation groups in a certain sense, so forth and so on. So there's all this crazy stuff that it can be, like, and so these objects, and that's what I think is so cool about this, is like abstract algebra lets us do algebra where we're not using numbers anymore. We can go into much more exotic locales, and we'll just start playing with examples here pretty soon. But I do want to define one or two more things, and then we'll just do problems. So integers are commutative, right? Like if we add two numbers, it doesn't matter what order we do them in, but this is not true for groups in general. So if the elements of a group, all of them commute, then we say the group is abelian. And that's named for, I think, Nicholas Abel was his name? I don't know. Abel was definitely his last name, and he was a Swedish mathematician. He died young. Big important guy early on in group theory. One of the biggest math prizes you can get is named after him, the Abel Prize. But anyway, and so it's really important. The whole reason I'm mentioning this, we're only going to see abelian groups today, and probably even next time too. But it's really, really important to just get in your head that, like, you cannot assume that you can just reverse the order of operations. And if you've taken, some math before, you've probably seen this with matrices, right? Like matrix multiplication is not commutative generally, right? Like if you multiply two matrices, the order in which you multiply them matters. And so there's this operation that's not commutative. It's also the abelian grouper. Hey, maybe that's where the thing came from. Woo. All right. So let's define the order of a group. The order of the group is just the cardinality, how much stuff is in it, right? So Z5 has 5 elements, so the order of Z5 is 5. The integers, on the other hand, have infinitely many elements, and so the order of the integers is infinite. It's pretty straightforward, eh? If we consider this next definition, it's very straightforward. It just gives us a notation. It's essentially exponential notation, right? It's very useful because sometimes we might want to multiply some or star some element with itself many times, n times in this case. So if n is positive, then, well, we always assume n is a positive integer in this case, right? So g to the n is just g starred with itself n times. G to the minus n is g inverse starred with itself n times. And then we just define g0 to be the identity. So in that regard, it's very much like exponential notation. In fact, as we get further along and start developing a little bit more robust skills in algebra, more and more I'm just going to go to that exponential notation, because you definitely don't want to keep writing star, and certainly when you're typing up like Beamer slides, you don't want to keep typing /star. But anyway, all that nonsense aside, so let's take a look at one last. This is the final definition, and then we'll just do practice problems. So here, I think I spelled whatever. Define the order of G. So if G is just some element in the group, we define the order of G to be the smallest integer n such that G to the n equals E. If no such n exists, then G has infinite order. Yep. And so this is, it seems sort of like maybe not that interesting right now. Like, I mean, the order of a group, obviously, like knowing how big it is probably useful. But knowing the orders of elements inside it is actually super important, because it lets us distinguish between different groups of the same size. So for example, there are 2 groups up to isomorphism with 4 elements in them, and they are not different. Well, they are different. they're distinct, and one of the ways you can tell they're distinct is the order of their elements. So for example, the Klein group has no element of order 4, whereas Z4 does. So that's a way to distinguish groups. So this order business is good stuff. Yes. Cool. So that's it for the little de facto lecture, or whatever you want to call it. For now, let's do some problems. Let's do it. So these problems here are pretty standard. Like, let's axiom check, yo. So for example, the first one says we have R star, which is the set of all non-zero real numbers, and then we have this binary operation there, x star y equals x times the absolute value of y. So we got to figure out if this is a group or not. So let's start with, is this a binary operation? So this takes 2 real non-zero numbers and multiplies one by the absolute value of the other, so you're not going to get 0. You'll always get a non-zero real number, so that is indeed closed. Let's try associativity. Let's see if that works. So how about, I don't know. Yeah, I think that might work. The problem is really going to come when you get to inverses, things like that. Like for example, -3. If we say that, let's say x equals 5 and y equals -3, for example. Yeah. So then, well, let's just think about what would an inverse of -3 be. So like, forget this. Let's try and find y inverse. Right? So again, it's what is y inverse under this funky star operation, right? So if if y inverse, so let's say we have y inverse star -3. What is that? Well, that's whatever y inverse is times 3. The absolute value of -3, which is 3, right? Oh, also, I guess we should probably note that what's the identity in this set? Well, it's number 1, right? Because either way, if I do 1 on either side, right, like the absolute value of 1 is always 1, so I'll have x times 1 or 1 times x. Ooh, or does the identity even work? Is there even an identity? See, I like doing problems like this on the fly because I don't know. Is there even an identity? So is 1... So 1 should be the identity. This also is going to break in a second, but yeah, this one's totally broken, right? If it's anything, it's going to be 1, right? Because we're multiplying stuff. So let's think about, like, what could it be? Like, so if we had, say, 1 star -3, well, that's going to be 1 times the absolute value of -3, which is 3. So that's not good, right? That is not an identity. See, the problem with this one is you're going to have a one-sided identity and a other-sided inverse. So, right, so, you know, this side will be fine. The inverse in this case, right, would just be, what, 1/3, right? But if we do it the other way, if we do -3 star y inverse, and it's -3 times the absolute value of something, right? Some real number, and there's no way that can be negative, right? So there's no way we can get to 1. So this first one here, this part A, this is not a group. No, no, no. Not a group. It's a liar. It's a phony. But the second one is just a slight modification. And the second one is r plus, which is just the set of all positive real numbers. So that's 0 up to infinity, not including 0. And in this case, we could check the axioms pretty quick because by assumption, these are all positive numbers here, right? And since these are all positive real numbers, star is just regular old multiplication. Because since y will always be positive, the absolute value of y is just y, right? So this is just multiplication. So really all we have to check is what? We have to check that there's an inverse and an identity. So the identity is going to be 1. Yeah. The identity is 1. I guess I should put, like, here's 1b. So in this case, e is 1, right? Our identity is 1. And then for, you know, if we take any number in there, r inverse is exactly what you would think it is. It's 1 over r. And because these are strictly positive real numbers, we don't have to worry about dividing by 0, so we're all good. Check. Here's a great classic example. The nth roots of unity. Unity! So the nth roots of unity. With all this discord in America right now, people talking about needing to unify, needing unity, man. Just start solving some complex polynomials, bro. That'll do it. Whatever. But anyway, the nth roots of unity, I'll denote them u sub n. And like it says on the sheet there, it's just a set of all complex numbers whose nth power is equal to 1. So let's just remind ourselves what the complex numbers look like, eh? So we've got the complex plane here, the x and the I, y axes. Yeah? And your general number, you know, is some point on this plane. And so what we need is find all the points that, we multiply them by themselves n times, and we get back to 1 here. So there's the point 1. And that is the actual number 1 on the complex plane, right? Because this is 1 plus 0i. And so what we see is that, if we think about all the stuff that, if it's going to get multiplied by this, the modulus has to have the same size as 1 in this case, right? I mean, this is just true. Like, if z to the n is equal to 1, then the modulus of z to the n is equal to the modulus of 1, but that's just 1. Yeah. So this thing has to be the size of 1, and you could also, another approach is to just use the Euler equations and stuff, but all the complex numbers... God. So here's, pretend that's the unit circle. The Elephant Man unit circle. And so any possible point that's going to be a solution to this equation is going to have to lie on this unit circle, because those are all the points that have modulus 1, right? They're the stuff that's exactly 1 away from the origin. So let's think about all the possible solutions. Let's do, say, U4, for example. Let's do a specific example, yeah? So in this case, this is all the stuff in the complex plane that when you quart it, you get 1. So let's try and figure out what's in this, if there's anything in this. I mean, I would say there's a pretty obvious thing in there. 1 to the 4th is obviously 1, yeah? So 1's in there. So we're not empty. We got a non-empty set. That's a good thing. Next, well, how about -1? Yeah? Right? -1 squared is positive 1. And then positive 1 squared is 1. So that's -1 to the 4th is positive 1. Yeah? I think there's more. In fact, I know there's more. There's 2 more. And based on where these 2 are, where do you think they should be? Well, yeah. Up here and down here. So up here is positive I, and down here is negative I. Remember, I is defined to be the square root of -1. Yes, yes. So then I squared is -1. I cubed equals -I. And I to the 4th, well, that's -I times I, which is -1, which is positive 1. So I is in there. And very similarly, it's the same argument, minus I is in there as well. And that's it. Generally speaking, the nth roots of unity, just think of a regular n-gon, one of whose axes is 1. And that'll give you essentially what the points are. You can use the Euler equation, right? Whatever. But really what I want to do here is just establish what this set is, right? So this is in the complex plane, and these are the only 4 numbers that if you multiply them by themselves 4 times, you get 1. Cool. So let's verify. Let's check the axioms. So the identity is 1, not surprisingly, right? Because we're by assumption we're multiplying here. There we go. Right? We're multiplying just in the normal complex numbers sort of way. And so this is obviously 1 times anything is itself, right? So we have the identity. Inverses. What about inverses? Well, well, 1 is its own inverse. -1 is its own inverse, right? Right? So -1 has an inverse. I times minus I. Well, what is that? That's minus I squared, so that's minus negative 1, so that's 1. So I and negative I also have inverses. Check. It's a group. Yep. The roots of unity. Next, let's take that same set of numbers, but now instead of just doing multiplication, let's change it to addition. So let's suppose I take these same 4 numbers, and let's say I just use standard addition. I don't even have to check if there's an inverse or anything. I know that's not going to work because, so if I take 1 plus negative 1, well, I'm going to go to 0, but 0 to the 4th does not equal 1. So this one is not. No. It is not. For the sake of time, I'll skip this one. This one's pretty, just think about it, right? Like the operation, we have a normal addition with these special sort of real numbers, right? You have 2 rational numbers plus one of them, that's right there. So it does make a group under addition, but there's something wrong with it currently to make a group under multiplication. So your homework, should you choose to accept it, is to figure out how to make that a group multiplicatively. Like, what do you need to do about it? Number 2 is a great practice induction problem. I won't do that one right now. Let's do something good. Well, sure, let's do this one. Let's show that if G star G2 squared is... Yeah, this is a really good one here. Let's do this one, number 3. Yes. I'm like, it's such a good problem that I wrote. Amazing problem. It's like incredibly useful and full of insight. What have you. Maybe this would be more interesting if I did a impression. So let's suppose... So here again, we're not making an assumption in this case that we're abelian, right? We just have a group. And G1 and G2 are in this group. Yeah. And we have, by assumption, that G1 star G2 squared equals G1 squared star G2 squared. Right. Yes, indeedly doodly. So yeah. So what do we want to show then? Then these elements commute, right? Yeah, G1 star. Now, this is not saying the entire group is abelian, but rather that these particular elements commute, yeah? Because again, this isn't for all G1 and G2, this is just for these. So let's start with this. What is this? Well, by definition, right, this is this thing starred with itself. So this is G1 star G2 star G1 star G2, right? But we also know that this thing equals, by assumption, G1 squared star G2 squared. So in a problem like this, so what do we want to do? We want to show this, right? This is our goal. We got to show that these elements commute. So, well, we have this thing equal to this thing. So let's multiply by some inverses. So I'm going to multiply both of the left-hand sides with by G1 inverse. Right? So we know G1 inverse exists because by assumption G is a group. G1 is in there, so G1 inverse has to be in there as well. So I'm going to forget this middle part, and I'm just going to do these. So we'll have G1 inverse star G1 squared star G2 squared. And that's going to equal G1 inverse star G1 star G2 star G1 star G2. Whew. But what happens here? So we know that because this is a group, star is associative, so I can reassociate here. So G1 squared is G1 star, so I can cancel one of those out. So I get G1 star G2 squared. And then the same thing here, I reassociate, so those go away. And that's going to be equal to G2 star G1 star G2. And then what do you think we do to finish it up? Multiply both right-hand sides by G2 inverse, right? So we'll have G1 star G2 squared star G2 inverse equals G2 star G1 star G2 star G2, oh my gosh, inverse. Right? These two fellas become the identity and cancel. So we get, those two do. And the same thing happens on this side. So we're left with, so what's left over here? We have one of the G2 squareds cancels with the G2 inverse. So this is G1 star G2. Over here, the G2 and G2 inverse cancel, and we're left with G2 star G1. Yeah! The people rejoice, Holmes. Yes, it's good. Whatever. Good. Moving on. That's pretty standard stuff. Yeah, good stuff. Good times. Relaxing times. Ooh. Let's do number 5. Number 5 is boss. This is a great problem. This is a classic problem. Or actually, I'll finish with number 5. Actually, I'm going to do number 6, and then I'll do number 5. So let's do number 6. So G is a group. H and G are elements of the group G. We want to show that the order of H is equal to the order of GH inverse. Cool. So let's just say, so by assumption, so we know G is a yeah. So we'll just do the case, I think, where the order is finite. Or actually, we don't even have to. So let's just notice, before I even do this, we'll come back to that. Let's just notice that GH inverse to the n. So here, again, I'm using this exponential notation. Assume there are stars in between there. Well, what does this equal? This equals GH inverse times GH inverse times GH inverse, right? N times. Yeah. But notice what's going to happen here. This is going to telescope, right? We have a G inverse followed by a G. So this first part's going to be GH squared G, and then we'll have another HG inverse, dot, 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 GHG inverse. But you continue this telescoping all the way through, and, you know, what do you have left? You get G times H to the N G inverse. Yeah? It's this really cool telescoping thing, right? Like, because they're lined up with a G on the left and a G inverse on the right, if you stick a bunch of them next to each other, all the G's and G inverses in the middle will just cancel each other out. And even though there's no assumption by a abelian nature here, yeah, this is simply a matter of all groups do this, right? This is just the way you line these up, and this is called conjugation. This is super useful, especially you get into like orbits and things like that, stable line, all these things. Super useful concept. But so what this means is, so notice that if, you know, H to the N sits inside GHG inverse to the N, right? That's just lives inside there. So let's maybe make a note of that. We'll just put that up high. So this is a fact, right? We just showed that here. So if, you know, so if the order, suppose the order of H is finite, and let's say the order of H is, I don't know, K, yeah. Well, by definition, that means that H to the K equals the identity element E, right? So then, if we take from this notion here, then G H G inverse to the K, well, that equals G H to the K G inverse, but H to the K is E, so that just equals G G inverse, which equals E. Yeah, I like that telescoping business. Telescope, telescope, telescoping business. Yeah. I don't know. I think it's pretty rad. Cool. And so what this means is, right, and then for the infinite case, right, well, that's a little trickier. I mean, obviously, if it really follows from this, but the idea is essentially like, you know, there's a little something potentially to worry about with H and G. I don't know. I think we're fine. It follows. I'll let you prove that in your own mind that the infinite case holds. Again, I made this disclaimer yesterday. I'm not a teacher. This isn't meant to be like, you know, you're not going to get a degree from this or whatever. But you'll gain lifetimes of enjoyment and satisfaction. I don't know. Math's pretty cool. So let's finish with number 5, and then I'll call it a week. And then I'll post this, and I might even post solutions. You never know. On a website, I'll post links and stuff and all that. Laters. Let's just do number 5 and call it a weekend. Okay, so let's do number 5 now. So G is a finite group, right? The order of G is finite, so that means there's only a finite number of things in it. And then there has to be an even number of elements with their own, that are their own inverse, right? So if there's something I meant to, it's not real hard to prove, but the inverses in groups are unique, as is the identity element. So in particular, if you have a single identity element, any other identity element is just the same. And if you have an inverse, if you have two inverses for some element in a group, then those two must be the same thing, actually. And so let's just notice that if G star G equals E, then G equals G inverse, right? This is a useful notion. I don't know how important it is going to be here, but it's worth mentioning here, I think. So let's think about, so G is even. For some, right? There's some, the order is 2 times something, right? Now let's consider a subset let's call it, I don't know. Let's consider a subset of G. And let's where S is the set of all G and G such that G does not equal G inverse. Yeah? So, right, so there are some elements that are their own inverse, right? But some that don't, and potentially, I mean, maybe they all do, who knows? This is all just sort of up in the air yet, like we haven't proven anything yet. But so let's just think about the size of these two sets relative to each other. So let's suppose that, I don't know, let's suppose little h is an element of this set S. Then we know that h does not equal its inverse. But by the exact same token, h inverse does not equal h, right? So if h is in this set, then h inverse also has to be in that set. And so what does that tell us? That tells us that everything in this set comes in pairs. So the order of this set, the cardinality of this set, I just want to be clear here that S isn't I'm not thinking of S as a group, I'm just talking about its cardinality here. It also has to be even, right? Because any element that's in here is going to have some other element to go with it. It's inverse, right? Because by assumption, it's not the same. So this, even if there's nothing in here, then the size of that is 0, which is also even. Yeah. So no matter what, the order of this thing is even. So then if we look at the size, let's look at the order of G minus S. Yeah. Whoops, the order of G minus the order of S, I should say. Sorry. Well, that's 2k minus 2l, which is 2 times k minus l, which is even. Yeah? Oots, 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 oots. What this shows even more, I mean, you could even phrase this question a whole bunch of different ways. This also makes an equivalence relation, incidentally, if you partition things this way. What this really shows is that if you have a group with an even order, there has to be one element, at least one element of order 2 in that group. In fact, and we can see that, let's go back to, if we go back to the roots of unity here, notice that -1 fits that bill, yeah? -1 and -1 are their own inverses, whereas the other ones you have to go around more. Sweet. Well, like I said, I'll post some stuff up and send links and all that. If you tuned in, I certainly appreciate your tunage. Much like that homeboy, what was that movie? Dark City. Yeah, he can tune. Anyway, I hope you'll tune in next week. Anyway. Well, for the two of you watching, cheers. Bye-bye.